take it away.
Indeed. Hello, everyone. Since computers are very hard, you're going to see my browser as well. Apparently, full screen is very hard. I can't find the F11 button. Hello, thank you so much for hosting me. Thank you to Anders and Wayne for their excellent presentations you had. Please do fasten your seatbelts and keep your hands inside the vehicle at all times. This is going to be a high-speed talk. I only have 20 minutes, and I am from Bergen, so that's the short end of a very short stick. On the bright side, it will be over soon, and there are loads of colorful pictures. Can everyone say their name on the count of 3? 1, 2, 3. Berge. Very good. Nice to meet you all. I'll try and remember your names. Also, every single picture in this presentation is of employees or former employees. There are actually no stock photos, I promise, in this little slide set. We will very briefly look a bit at what urban sharing does, how we are cloud native, and then we're going to talk briefly about how the cloud is just someone else's computer. My name is Berge Schwebs Bjørlo. I call myself a site reliability engineer, mostly because I need a title. In practice, I do a bit of everything, and I keep putting my fingers into moving machinery, as we do. I've been with urban sharing since the very beginning of the company in 2016, and I will accept approximately equal amounts of blame and praise for the infrastructure that we have today. So, what does urban sharing do? We're a small company where I have 12 employees in my notes, and then I asked, and it turns out we're actually 14 employees. We're based in Oslo, but more than half of the company is remote, including me. I live in Trondheim, not in Oslo. And we sell micromobility technology and management system. Micromobility is a very Western term for sort of personal transportation with small things, that being bikes or e-scooters, but apparently not rickshaws and not mopeds, unless the mopeds are electric, in which case they are micromobility. So it is a bit confusing. But most of our customers are in the city bike business. So that's what we're going to talk about here and have use examples here. So a typical customer of ours, so we're a B2B thing, so a customer of ours will be an operator who owns bikes, and they own city street infrastructure and so on, and we provide all the rest, the software mostly. So that's kind of the things we have. So how does it work? Typically a person, this is Mauro, one of the original principal developers, will open their app and say, oh, I would like to go on a bike trip. Sounds like a wonderful thing to do. They'll click unlock or request a bike. Then the bike will unlock, or the station will unlock the bike, depending on the system and the hardware on the street. And then the user can go on a delightful little trip in Oslo. And when they're done with their delightful trip, they'll return the bike, and then they'll get the notification in the app, and maybe we'll charge them, depending on if it was an electric bike or whatever, and so on. So that's what we do. How hard can that be? And it turns out it can be surprisingly hard, or at least surprisingly complex. There is a lot of stuff. So our customers are companies, and they operate city bike schemes. So in Oslo, there's something called Oslo City Bike, Oslo Bysykkel, and the company that owns that is a customer of ours. The company is called UIP, and the UIP has a contract with the city, with the municipality of Oslo, and they own the bikes, and they employ the bike mechanics and so on. And then from us, they buy technology. Right? They buy the end-user apps, the websites, the payment, the back-end system, the back-office system, the UIs, the software, the firmware that runs on the actual stations, and so on and so on. We store data, we provide analytics, we have loads of stuff, and that's from the sales deck. This is not the sales deck. For some customers, we actually also design the electronics and locks, and the mechanical components. And in some cases, we actually design the bikes. So some of the bikes that are on the streets in Oslo are designed in-house in urban sharing. And for other customers, we integrate with a large number of various third-party devices. So we have support for different kind of e-bikes, different kind of bikes that can lock to themselves. We have support for 3 or 4 different e-scooter vendors, and so on. This is an actual image from our actual office in Oslo of an actual software developer. His name is Paul. He's debugging software. That's how it looks when you debug software when you're in this business. But I digress. We're here to talk about computers in the fog. This stuff all adds up to a lot of complexity. So this is a simplified, high-level overview of the current architecture. It's going to be a short quiz afterwards, and I expect you all to be able to draw about 80% of this diagram when you're done. And all of this on the right-hand stuff here runs in Google Cloud. But it is hard to see computers or anything really in the cloud. And the computers are someone else's. Cue dramatic music. Very nice. So after this very dramatic intro, we're going to briefly go back in time for the right 2002 mood. Please imagine Eminem for this little part. In 2002, the Oslo City Bike scheme was launched, along with a number of similar schemes in different cities around the world, mostly in Europe, but also in South America. It had custom hardware, and at the time, it was quite revolutionary. The stations communicated with their backends over SMS. The users had RFID cards to unlock bikes. It supported offline mode. It had touchscreen UIs. It was all quite modern at the time. This picture is of Milano, where the operator is also a customer of ours. And this is an even earlier version of what is currently in Oslo. So it's been iterated over the hardware design. By 2016, this system had grown. In Oslo, it had now a web page, very modern, an app, online payment systems. We got rid of the RFID cards. The first year that City Bike, used to mail RFID cards to all of the users, like 50,000 users in the mail. The first year they introduced the app, they mailed 25 cards. Nobody wants to use an RFID card. Most of this work to extend this stuff and make it modern was done locally by the company that owns Oslo City Bikes. And the backend systems were still monolithic Windows applications written in Delphi. Can I have a show of hands? Everybody who knows what Delphi is? Yeah, it's about a third of you know what Delphi is. It's object-oriented Pascal. We still have Delphi code running in production, and it works beautifully fine. All of this did run in AWS, but it ran like a brick-and-mortar kind of data center thing. Right? There were VMs, but they were hand-managed as if they were just servers that were put in a rack. It had no multi-tenancy. It had multiple sources of truth of data. There was like several database copies in different vendors, and there were different providers of stuff. Some stuff was running on Heroku, some stuff was running on AWS. Just opening the system in the spring or adding a feature or just keeping it running was an anxiety-inducing exercise. Right? It was barely keeping up. There were reliability issues, there were scalability issues, there were data integrity issues, and there were customer expectation issues. Some of you might have lived in Oslo in 2016, where there was loads of press, let's call it that, about the City Bike system. However, this transformation into an app-based and user-centric thing was a huge success. Right? With the introduction of the app, the number of trips in Oslo grew by 2 orders of magnitude year over year. So by the end of 2016, there was 1 million trips. It was 2 orders of magnitude more than the previous year. Thank you for coming to my TED Talk about how technology choices is not what leads business. So by 2016, bright minds had reasoned that this might be a repeatable success. Right? What if there was a provider that could offer an end-to-end software stack with everything from an app running to the firmware running on the actual streets? Turnkey solution. You could get us on as a customer. You get new features all the time, right? Continuous development. All the cities using the same system could benefit from the new features. With scale internationally. That'd be really grand. So that eventually became urban sharing. That meant we had to make technology choices, right? And how do newfangled startups architect their modern software solutions? We had a small team, and we wanted to do a lot of things. So from the very beginning, a leading design principle was that we are going to use managed services from a cloud provider as much as absolutely possible. And this is what I believe they now call cloud native. We reasoned that Google, they're very good with distributed systems. They're very good with operational capabilities. They have very good load balancers. AWS does not. And the pricing was good. So we thought, okay, we're going to go with Google Cloud. It's the underdog. It used to be the underdog. I suppose it still is, to the extent you could call the $15 billion business an underdog. And they also provided a managed version of this new cool thing, Kubernetes. Early in 2017, first commits were made. We decided upon having a single source of truth and keep all the state in a Postgres database, and everything else would be approximately stateless. So we could almost trivially just run everything in a classic Kubernetes setup with stateless deployments and stateless pods. And these are containers, as you can see on the picture. Kubernetes gave us all the goodness that it's in the sales stack, right? We had zero downtime deployments, we had easy rollbacks, we had horizontal scalability, and we got all that stuff that you get from your typical Kubernetes setup. But being cloud native, we really wanted to go all in the fog, as I call it. When we said we didn't want to reinvent the wheel, we really meant it. So we were using, and we still are using, Kubernetes, also Cloud Memory Store, PubSub, Cloud Scheduler, Dataflow, BigQuery, Stackdriver logging, Stackdriver monitoring, Stackdriver error reporting, Cloud Debugger, Cloud Trace, Cloud Load Balancing, Cloud Armor, Cloud DNS, Cloud VPN, Cloud Router, Cloud CDN, Cloud Build, Cloud Container Registry, Cloud Endpoints, Cloud Storage, Key Management Service, and Cloud Security Scanner. And these were only the ones I could bother with finding icons for this little slide. And dear Google, please stop prefixing all the products' names with cloud. We had no single points of failure. Everything was replicated, everything was duplicated, and most things were written from scratch to run in the cloud development. It is, as the cool kids say these days, cloud native. We had Postgres running in Google Cloud SQL. It had replication, it had backups, it had automatic failover. What could possibly go wrong? Cue dramatic music, this time in a minor key, please. Google, one day, wanted to replace some actual physical switches in their brick-and-mortar data center, and then they triggered a control plane network isolation condition. And that is an error mode that Cloud SQL just doesn't support, right? We had loads of tickets with this, and no, we're just going to fail. That means that Google, the inventors of Paxos, the champions of consensus algorithms designed for failure, they failed to design for failure. Right? This is what a rack of Google Cloud switches look like. These switches are part of a system called Jupyter, which is an in-house networking and switching thing built at Google. It's really cool. They've published some really interesting papers on this. Really cool. But at the end of the day, this is a rack with switches in it. The switches run on power. The humans patch these things. And like every other thing, they fail. Right? Hardware fails, either on its own or when humans interact with it. But nevertheless, we kept at it. We eventually moved away from Cloud SQL to actual Postgres running on VMs instead. So we traded that complexity for a different set of complexities. We were featured in the Google Cloud marketing material. Spoiler alert, that does not help with your cloud build, and it does not help with your support tickets. And our users were biking as if there was no tomorrow, which is slightly ironic, since biking helps with actually being a tomorrow, for humans at least. And we got new customers, and we grew. Even though everybody loves war stories, this is actually not to talk about war stories. Also, urban sharing didn't fail, but there are failures. I want to talk briefly about how cloud-native systems, even when they're greenfield, architected consciously, using modern methods, this is following vendors' guidelines, this is best practice, this is really modern stuff, written from scratch, also fails. I'm not saying this to trash talk Google Cloud. On the contrary, Google Cloud is actually a pretty solid platform. It's just that complex systems are hard. They're really, really hard. Complex systems have complex failure modes. And if a tiny bit falls out in an unexpected way or at an unexpected time, cascading failures can occur. And they can be really, really hard to debug. We write postmortems for all our outages and incidents. They're mostly a fun read, at least when the dust has settled and the customer has forgotten it and you've paid your SLA dues. And like everywhere, loads of different things are happening, right? And for wildly different reasons. But I will argue that there are two main factors involved in almost all of these outages. Factor one, it's not your computer. Or rather, there are issues outside your control. It could be a bike that's not working as intended, as Julia is observing here. And I promise, these are not stock photos. These are actually our employees. This is Julia. When something outside your control happens, there's nothing you can do. right? When there's a cloud system. This is, of course, true for any kind of system, but the more abstract service you're using, the more stuff is outside your control. Here's an example. When the foggy networks goes dark, you're also in the dark. This was an outage a few years ago, and we had no idea what's going on. Everything went down. We couldn't access the Kubernetes control plane. We couldn't access the monitoring. We didn't get any alerts because alerting was down. We couldn't access our own tooling, right? We could see that physically, people on the street, if you looked out the window, people could use our service. That was the indication we had. We had no idea what was going on. This message here was posted weeks later when Google posted their postmortem, the public postmortem. We were completely in the dark, right? In December 2020, Google had a failure in signing into Google accounts, and then they said, some services might be affected, which is like all of them. Because every single service in Google Cloud, if a human needs to access this, the OAuth2 thing needs to work. And they had a problem with Chubby, which is their distributed log manager thing. And we couldn't access anything, right? Nothing at all. There was stuff running, and some of that was working, but we couldn't access it. We were absolutely blind. A few years back, AWS had a famous S3 outage. They had several, actually. There was a typo in a comment that brought down S3. AWS had never, ever rebooted S3, right? And they had built much stuff up on top of it. And that includes the AWS Health dashboard and their public incident thing. So that said, oh no, everything's fine, because they couldn't access it, right? Google services went down when S3 went down. And these examples are with networking, cloud networking, but it is true for many other things as well. A lot of the product in a public cloud is built on top of other products in the same cloud. In AWS, almost everything runs on EC2, the VM thing. In Google Cloud, almost everything uses Chubby, the distributed log manager. There are turtles all the way down here. And so many of these turtles are stuff that you don't have any sort of visibility into at all, or any way you can control it. Factor 2, it's neither Jasmina nor Tobias. It is complexity. Even though I'm quite proud of what we've strung together at Urban Sharing, and it most of the time works pretty well, I have continuous regrets about the level of complexity that I've been part of introducing into this. And keep in mind, we're a small company. We're 14 people. We don't have a 50-strong team just to support the IT stuff, right? We're 14 altogether. This, obviously, is a map of the Dutch city Berge-Nassau. That was Dutch. Also, the Belgian city of Berge-Arton. I don't speak Dutch nor French. These cities, for various historical reasons, have borders that are now an absolute patchwork, right? These are cities that have enclaves within enclaves within enclaves. So the outer enclave here, I can't even remember if it's Belgium or the Netherlands, but it's kind of countries inside. The borders go through roads, they go through buildings, they go through shops. This is a particular problem during the pandemic because Belgium and the Netherlands had different rules for when a shop could close and open and whether they could sell alcohol and so on. So shopkeepers had to close half their shop, right? Because the border went through it. They have different tax rates depending on what you buy. It's immensely complex. This is a simplified view of the Google Cloud services. And it strangely resembles Berge-Nassau, right? There are complex interactions between all of these, not all of them, but a lot of these components. And they build upon each other, and they change because Google changes their product, and they develop stuff and launch new stuff, and then frequently they deprecate old stuff. And this makes it hard to do the one thing that I consider the absolute most important thing about a system, and that's reasoning. In order for humans to debug systems and understand systems, we must be able to reason about the systems. Because once you know not just what a system is meant to do, but how it's meant to do it, then you can reason about any state of the system. And once you can reason about it, it's not magic anymore. In 2011, I had the privilege of supporting moving the Norwegian encyclopedia, which is called Store Norske Leksikon, which is kind of Encyclopedia Britannica, except smaller and in Norwegian. We were moving it to a new home. It was a new organization taking over it. So we ordered 3 servers, physical servers with a Norwegian hosting provider. We had them put in a rack. We had them wired up to the internet. And the total cost of these servers was 6,000 kroner a month. That included hosting, power, connectivity, network, all of it. Then we installed Debian on them, and we installed Postgres on one of them, and a Rails application, Nginx and Varnish on the other, and that was it. It was super trivial. And it turns out these servers were also vastly overpowered. But it was dead simple. There were no task queues for cron jobs. Right? There were no complex failover systems. There were no load balancing. Yes, we had a few seconds of downtime every time somebody deployed a code update. That was mostly hidden behind Varnish anyway. Yes, we needed to restart Varnish or Nginx every now and then. A few seconds there, a few seconds there. Every now and then you need to do kernel upgrades or whatever, so you need to reboot the servers. We scheduled a maintenance window, and then we rebooted. 10 minutes later, bam, up. And this system ran the third most trafficked site in Norway for years. For years. At 6,000 kroner a month. And that was, they probably ripped us off a bit there. The customer was wildly happy. It was super available. It was really robust. It worked really well. And I can bring up any kind of person who's reasonably familiar with Debian or a Linux-based system. I could bring them up to speed in 20 minutes. It was so simple. It was super simple. And once during network outage, we just sent someone there who patched it over, moved the network cable into another switch, bam, up again. Would I have designed the same thing today? Probably not. And as it were, that encyclopedia is now actually running on Google Cloud. But the system made for a very robust, very reliable, and very cheap system. Right? It wasn't without problems, because everything breaks, but we could fix it. And we had the visibility, and we had the insight. And it was so simple that people can understand it in less than half an hour. Yes, we paid for it. We had small windows of unavailability, right? And we did risk hours of unavailability. If the hardware actually broke, we'd have to move it onto the spare server we had there. That would take us a few hours, right? It was a cold spare. But that was the price we paid, that risk. Simple is reliable. And on my very best days, I strive for the same level of simplicity when designing for things in the cloud. But sometimes, you should rather just go out on a bike instead. Thank you very much.